everybody, welcome to another video. Hope you're ready to flex those brain muscles. Today we're going to solve some systems of linear equations using substitution. So this is a way we can solve systems of linear equations algebraically. So let's go ahead and get right into it. First of all, what does it mean to solve a system of linear equations? Do we remember? Well, graphically it meant to find the intersection of these two lines, right? These are just lines. But algebraically what it means is we need to find numbers for x and y that satisfy both of these equations simultaneously. And another way to think of it is I need to find a number that I can plug in for both these x's and a number that I can plug in for both these y's that make this a true statement and this a true statement. And what I mean by a true statement is something like 8 equals 8. -4 equals -4, something like that. That's a true statement. So how do I do this? Well, using substitution, the first step is I take either one of my two equations and I solve for one variable. So either x or y, just whichever one is more convenient in either equation, right? And what I mean by solve by is I'm getting that variable by itself on one side of the equal sign. So let's go ahead and do that. I'm going to do it to this second equation. I'm going to solve for y. So I'm going to add x to both sides. And again, you could have done it to the first equation. So let's see, that gets rid of this x and that gets the y by itself. So I've solved for y. Okay, so the hardest part about substitution is understanding why this works. Why is it that we substitute in this for this? And the best way I can think of it and the best way I can explain it is that we have two constraints for y. And a constraint just means like a restriction. So what I mean by that is, think about it. Any number we pick for x, we can pick any real number for x. Y has to be 4 less than that number, right? That's a constraint. That's a restriction for y. But this is also a constraint. So y has to be 4 less than x, but y also has to be something where when you add x to it, you get 8, right? Because we're looking for numbers that satisfy both of these equations simultaneously. So since we need to satisfy both of these, we can replace this y with x minus 4, and we can solve for that x. And that x is going to be the x value that satisfies this equation. And we can find the y value by plugging that x value back in at the end, which we'll see. We'll go ahead and do this. So I'm going to replace this y with x minus 4. So x plus, and I always put parentheses, even though sometimes you don't need them, but sometimes you do. So I just always put them. And again, I don't need them in this case since it's just addition and subtraction. So I have 2x minus 4. All I did was combine my like terms. X plus x is 2x. And that equals 8. Now I'm going to add 4 to both sides. I'm solving for x, right? So 2x equals 12. So I need to get the x by itself. I divide both sides by 2. And I'm left with x equals 6. So this is the value for x that will satisfy both of these restrictions, both of these constraints for y. So since I have my x value, I can just plug this in really wherever to any x I want. But I choose to do this one since y is already solved for, right? So y equals x minus 4. In this case, x is 6. So y equals 6 minus 4, which is 2. Y equals 2, and you can write it as a point as well. Alright, so unfortunately I don't have room to keep this up throughout the whole video, but we can go ahead and break down the steps of what we just did, and these are the steps we're going to use for the remaining examples in this video. So, first step, solve for x or y in one of the equations. So either variable in either equation, whichever one is most convenient, okay? Second step, substitute what you get into the other equation. So whatever you get from solving for x or y, you substitute into the other equation like we just did. Step 3, solve for the remaining variable. So doing this will eliminate either x or y. It'll eliminate a variable so you can solve for whatever the variable is that's left. Step 4, substitute in that solution back in to solve for the second variable. So take this solution for x or y and go back to one of the original equations and plug that in to solve for the remaining variable, and those two solutions will be your solution set for this system of linear equations. Alright, so before we continue, if you saw my graphing video, we determined that there were 3 possibilities when we're solving these. Either we have one solution, no solution, or infinitely many solutions. So that's still the case. Even though we're solving these algebraically, it's still going to be one of those 3 possibilities. One solution, no solution, or infinitely many. So by the end of this video, we'll have identified how to determine which one of those cases it is, and we'll come up with, we'll do a little review and make sure we fully understand. But I think you'll see that it's pretty simple, and it's straightforward to identify which of those three cases we have. So let's go ahead and get right into it. Another example. So what should jump out at you from this? And maybe you're already seeing, okay, this is the equation I'm going to use and this is what I'm going to solve for. But if you don't, the general rule I use is that anytime I see something with a coefficient of 1 and I have a system of two equations, I just go ahead and use substitution and I solve for whatever that variable is, right? So I'm going to solve for x because it's easy. I don't have to divide by anything. I don't have ugly fractions. I literally just subtract 3y from both sides and bam, right? I've solved for it. So I'm going to go ahead and do that. Minus 3y minus 3y, and that gives me x equals negative 3y plus 5. So now this is what I'm going to use to substitute into the second equation. So I have 2 times negative 3y plus 5 minus 3y equals negative 8. Now I'm going to distribute this to, this is why the parentheses are important, right? Negative 6y plus 10 minus 3y equals negative 8. That's what happened when I distributed 2. 2 multiplied to both these terms. Now I can combine negative 3y and negative 6y. That's negative 9y. I still got the plus 10 there. And maybe you could have done both of these in one step, but now I'm going to subtract 10 from both sides. Minus 10 minus 10, I got negative 9y equals negative 18. Now I can divide both sides by negative 9, and I should get the y by itself by doing that. So a negative divided by a negative is a positive, and 18 over 9 is 2, so I have y equals positive 2. So again, here's another tip. You can substitute this back into any y in the original, but I always use this because we're already solved for x, and that's what we're trying to find when we substitute this back in, right? We're going to substitute this back in and solve for x. Well, this is already x equals stuff, right? So that's why I always just plug in right here. So I'm going to do x equals what? Negative 3, and my y is 2, so I plug in 2 for y, plus 5. This is just negative 6 plus 5, that's negative 1. So I have x equals negative 1, and if I want to write it as a point, I can write it as negative 1 comma 2. So in this case, we have what? We have one solution, right? Just like we did in the first example as well. All right, so for this example, I could probably solve for x or y in the second equation. I'm going to go ahead and solve for y. Since this coefficient is positive 1 and this one is negative, I can add x to both sides. So that's what I'm going to do. Plus x, and I'm left with what? Y equals x plus 3. So now I'm going to substitute in x plus 3 where this y is. And what do I get? Negative 3x plus 3 times x plus 3 in parentheses equals 4. So now first I'm going to distribute this 3. So I have negative 3x plus 3x plus 9 equals 4. Look, I have like terms, but wait a minute. Negative 3x plus 3x, those just cancel, right? That's just 0. So what am I left with? 9 equals 4. So I'm left with this statement, which is clearly not true. 9 does not equal 4. 9 never equals 4. So what this means is we have two lines that are parallel. There is no solution to this system of linear equations. So anytime you get something that doesn't make sense, that's not a true statement, this means every single x and y that satisfied this equation does not satisfy this equation, and vice versa. All the x and y's that satisfy this do not satisfy this. They're parallel lines. So no solution. And another word for this, what do they use? Inconsistent. It's an inconsistent system of linear equations. All right, so here I got y with a coefficient of 1, so that's what I'm going to solve for. So I'm going to subtract 2x from both sides. Minus 2x and minus 2x. So I'm left with what? Y equals negative 2x plus 4. Okay? So now I'm substituting in negative 2x plus 4, and I'm replacing this y in the second equation with negative 2x plus 4. So let's see, negative 6x minus 3 times negative 2x plus 4. Negative 2x plus 4 equals negative 12. So now I just distribute, but we got to be real careful. This is where a lot of mistakes are made, right? Negative 3 distributes to both these terms. Negative 3, all right? So negative 6x, negative 3 times negative 2x is positive 6x. Negative 3 times 4 is minus 12. Negative 12, right? Equals negative 12. So be real careful when you have a negative out in front and you're distributing. The negative comes with it. So now look, we have a similar situation as the last example. Negative 6x plus 6x. These cancel. But now we're left with what? Negative 12 equals negative 12. So in the last example, we were left with a statement like this that was not true and was never true, right? And that meant that we had no solution to the system of linear equations. It was inconsistent, right? So in this case, we have a statement, negative 12 equals negative 12, which is always true, which makes this a dependent system of linear equations. In other words, these are the same line. If you graphed them, they would be the same line. They would be layered on top of each other, if you want to think of it that way. So every single x and y that satisfy this equation also satisfy this equation. So we'd say infinitely many solutions, and you could also call it dependent. Alright guys, that's it for the examples. If you want to see more examples, please let me know in the comments below. I could potentially make another video with just a bunch of examples worked out. But let's go ahead and wrap up this video and we'll go over the 3 cases, right? One solution, no solution, infinitely many solutions. So with one solution, we're able to solve, right? We can solve for x or y, whatever variable we get at first, then we can substitute that back in and we can get a full solution. That means we have one solution. And we also call this independent and consistent, okay? With no solution, we end up with something that's just nonsensical, right? Something that's never true. 2 equals negative 4. That's not true, right? No solution. And we call this inconsistent and independent. With infinitely many solutions, we're left with something that's always true. Negative 12 equals negative 12. 5 equals 5, something like that. So this has infinitely many solutions, if this is the case, and we call this dependent and consistent. And again, just to review, independent just means that they do not share all solutions. So the only case that's not independent is when they do share all solutions, and we say that's dependent. Consistent just means there is at least one solution. So the only case that is inconsistent is the one where there is no solution. The other two are consistent, okay? So that's just a review of that vocabulary. Not every teacher teaches that vocabulary, but it's good to know. So hopefully you enjoyed this video. If you did, please hit like, hit subscribe, stay tuned for more videos. Keep flexing those brain muscles, and I'll see you in the next video to make some more brain gains.